So in this video, I want to go over a few examples of how to solve logarithmic equations. I may make another video later solving exponential equations, but for now, this is specific to logarithmic equations. So I have an example here. This is from the textbook. This is number 48 on page 233. And it says the natural log of x minus 7 is equal to 0. And we want to go through the process of how to solve this. So the first thing you need to do is you need to get the logarithmic term by itself first. So this log term needs to be on the left-hand side by itself. So I'm going to add 7 to both sides so that I get the natural log of x is equal to 7. In your textbook, it mentions a process of something called exponentiating. Exponentiating means that we cancel out logarithms by raising the sides to a base. So for example, the base of ln, although we don't write it, is e. So if I exponentiate both sides, I'm going to say e raised to the ln of e, well, ln e7, or x, and then e on the right side. So by the inverse property, it states that if you have the same base in the exponent as you do the logarithm, then they cancel. And so the only thing left on here is the x. It comes down is equal to e to the 7th, which is approximately 1096.633, and we'll just stop at 3 decimal. Oh, 1 second. This should be 96.633. But I would much prefer you leave it as a exact form. Don't do the decimal. All right. So let's look at another example. All right, so here's our next example. It's number 54 in the same section. It says 4 times the common log of x minus 6 is equal to 11. So again, I need to get the logarithmic piece by itself. So in order to get rid of this 4 in front, I'm going to divide by 4, which allows me to cancel those. So I get log of x minus 6 is equal to 11 over 4. Again, to get rid of logarithms, I need to exponentiate. So if I remember, the common log has base 10, then when I exponentiate, the base is going to be 10. So that allows me to cancel due to the inverse property, and I have x minus 6 is equal to 10 to the 11 over 4. Alright, and then I can add 6 to both sides. So I get x equals 10 to the 11 over 4 plus 6. This is just, again, a decimal. So we could just leave it like that, and that would be the exact answer. We could also get a decimal approximation for it. And that decimal approximation would be approximately 568.341. So WebAssign may ask you to go to 3 or 4 decimal places, so this would be what you'd put in WebAssign. But personally, I would prefer if you stopped right here at the exact answer and left it like that. Alright, so we're going to look at another example, and this one we're actually going to use the properties of logarithms to solve. So let's look at one of those. So again, on page 233 of your textbook, number 58 is this problem. It says the natural log of x plus 1 minus the natural log of x minus 2 is equal to the natural log of x. And we want to figure out what x would satisfy this equation. So the first thing I see that could be problematic is the fact that we have this minus here being separated, or separating these two natural logarithms. One common mistake that is made So one common mistake that is made is that students want to cancel the LNs in the first step, and that is bad. Okay? Do not cancel the natural logs in the first step. I know it's really natural to use the one-to-one property, but you can only use the one-to-one property if you have ln of stuff is equal to the ln of other stuff. There has to be a single ln on each side. Okay? Well, that's a problem here because there are two ln's. So we can use the properties of logarithms to combine it so that we can use the one-to-one property. So remember, the property allows us to take subtraction of two logs and make it division of the arguments. So this could actually become the ln of x plus 1 all over the all over x minus 2 is equal to the ln of x. And this is the quotient property. Okay? Now that we have ln, a single ln on each side, by the one-to-one property, I can cancel these out and just have x plus 1 over x minus 2 is equal to x. And again, I don't really like fractions when I'm trying to solve a math problem, so what I'm going to do is multiply both sides by x minus 2 so that I can get that to cancel and be left with x plus 1 is equal to x squared minus 2x. This brings my problem to just be a quadratic. Remember, if we want to solve quadratics, I got to get this equal to 0. Okay, so I can move the left-hand pieces over to the right and have 0 equals x squared minus 3x minus 1. And from there, we're going to have to solve this. Now, here's the problem. This particular quadratic is not factorable. So how am I going to solve it? I'm going to have to use the quadratic equation. Alright, so here's that quadratic from the last slide. So we're going to go ahead and start solving this. So we get x equals negative 3 plus or minus the square root of negative 3 squared minus 4 times 1 times negative 1 all over 2 times 1. So that's going to be 3 plus or minus the square root of 9 plus 4 over 2. And that's going to be 3 plus or minus square root of 13 over 2. Alright, so we've got two answers here. We've got x equals 3 plus the square root of 13 over 2. I'm going to say or, and I'm going to explain that in just a second, or 3 minus square root of 13 over 2. Now the reason I say or is because one of these solutions may not work. So if we go back and look at our original equation, let me go grab that and put it on this slide. Alright, so I got the equation here, and if we look at it, we got to think about what's the possible domain. And I really need to look at the domain of each of the pieces. So the first one we've got right here, we've got x minus 1. So with logarithms, you've got x plus 1 must be greater than 0, which means x must be greater than negative 1. So that's the first piece. The second piece says that x minus 2 must be greater than 0, which means x must be bigger than 2. Well, which of these is more restrictive? I guess I should say basically which one is larger. So 2 is larger than -1, so I can't plug in like 0, so that's out. So I have to be strictly greater than 2. Then the third piece says, well, that means x has to be bigger than 0. But x already has to be bigger than 2, so it's out. So the domain is all real numbers greater than 2. So we have to be wary, is one of these roots that we got less than 2? Alright, so we got to plug these into our calculator and actually see if they are, one of them is, rather, less than 2. So I put both of them into the calculator, and I get that the first one is about 3.303. Okay, good. It checks out. It is larger than 2. But when I plug in the second one, I get negative 0.303, and it does not check out. So we exclude it. This is a special type of solution. And it's called an extraneous solution. Extraneous solution. An extraneous solution is a solution that works out in the math, but when you go to plug it back in, it doesn't work. So if I went and plugged in x equals 3 plus square root of 13 all over 2 into my equation, then I would find out that it does satisfy the equation. But if I go plug this one in, I'm going to get an error because it's not inside the domain that I need. So we have to exclude it and say that the answer is just x equals 3 plus square root of 13 all over 2. And I would report that 3 minus the square root of 13 all over 2 is extraneous. But this is the only answer that satisfies the equation that I had. Alright, so let me do one final example that I don't see any like it in your textbook, but I do think it is a good example to begin. The closest thing to this one would probably be number 61 on page 233. But it uses the division again, and I kind of wanted to do one with addition in there so that we use the product property. Alright, so again, the first thing I need to do is I need to combine these two logarithms into one so that I can exponentiate. So if I do that, based on the product property, that says that this becomes the log base 4 of x minus 2 times x is equal to 3. So that's log base 4 of x squared minus 2x is equal to 3. So now that I have a single logarithm, I can exponentiate both sides, and here the base is 4, so I'm going to say 4 raised there and then 4 raised there. So the inverse property says those will cancel, so I get x squared minus 2x is equal to 4 to the third, and I'm thinking that's 64. Okay. So again, we have a quadratic equation. So to solve that, I need to get it equal to 0. So on the next slide, I'm going to have x squared minus 2x minus 64 is equal to 0. I don't believe this factors either, so let's just go ahead and plug it into the quadratic formula. X equals 2 plus or minus the square root of negative 2 squared minus 4 times 1 times negative 64 all over 2. So that's going to give me 64 times 4 plus 4, which is going to be 2 plus or minus the square root of 260 all over 2. So I have two possibilities. 2 minus the square root of 260 over 2, or 2 plus square root of 260 all over 2. And I could probably break that down, but for right now, I want to figure out which is a solution to my equation. So again, let me go grab the equation so that we can look at its domain. Alright, so we've got the three pieces we need to, well actually this one only has two pieces. So the first one is, when is x minus 2 greater than 0? Well then that's when x is greater than 2. And this one says, well, when is x greater than 0? It's just greater than 0. So I noticed that 2 is larger than 0, so everything has to be at least as big as 2 and bigger, because we can't be equal to 2. So the question is, which of these two is greater than 2? And just by eyeing it, I'm going to go ahead and say this one without much check, because this is likely going to give me a negative number. Just by inspection, I can see that the square root of 260 is going to be much larger than 2, making that negative divided by 2, which is negative, definitely not greater than 2. So our answer is going to be 2 plus the square root of 260 all over 2. And that would be the solution to this particular logarithmic equation. And I can break that down and maybe make it look a little prettier if I wanted. But just as an example, that would be our answer.